Hey, good morning, everybody. Hey, welcome to Parallelogram Physics Classroom. Okay, today we will be going through another past year paper. Okay, the paper I have chosen is Parallelogram Mathematical School. Okay, it's a prelim paper last year, 2021, for the Express, Sec 4 Express student for combined science. Okay, science physics. Okay, so if you don't have the paper, okay, I have shared it in my Google Drive. Okay, the description of my Google Drive is the URL for my Google Drive is in the description panel below. Okay, feel free to click on it to download the paper. Okay, if you have done it already, okay, now I think it's a good time to check your answers to see where are the gaps or where are your careless mistakes so that you can actually touch up, okay, can bridge the gap so that you will be ready for the up and coming O-level exam. Okay, so here we go. Now for this paper, okay, let's take a look. Now for paper 1, okay, now for those who have done the question, okay, let me zoom in first. Okay, for those who have done the paper, okay, this is the answer. Okay, you might want to pause the video here to just check answers to see how good you have done for your paper 1 MCQ. Okay, because remember paper 1 MCQ you have to score, I would say, a minimum of like 15 to 16 marks upon 20 questions, so that you can actually use your paper 1 answers, your marks, to actually value add your grades. Okay, to push your grade 1 level higher. Okay, so I believe, okay, you already have checked your answer. So let's go through some of the questions we have for this paper. Now, question one deal with the correction, zero error. I will not say zero error. Yeah, sorry, it's a zero error corrected readings. We have to use to factor in the zero errors and to factor in your observed reading and how these two readings actually is being used to get the corrected readings. Okay, so I will not dwell too much on the usage of looking at the micrometer screw gauge, because this particular segment, let's say using micrometer screw gauge error corrections, you should have done in your your Sec 3 first topic, chapter 1, which is is one of the, I would say, it's the simplest. It's a simple concept that we are looking at. Okay, so I will not dwell too much here. So, but if you need like the a refresher course on using a micrometer screw gauge or looking at zero errors, okay, you can look at my the video of my micrometer screw gauge and vernier caliper. Okay, I have a short video on how to use these two instruments, okay, in your chapter 1. Okay, feel free to double check or revise your this particular concept. Now, question 2, I would say, is an interesting question, whereby it looks at the description of the graph, or velocity time graph, but what is slightly different with other question is that instead of asking you to describe, okay, they actually ask you to look at it in terms of the gradients, or look at it in terms of the accelerations, and to actually ask you to choose, not just describe one section, it's actually to describe the 3-section graph. Okay, now for velocity time graph, you look at acceleration. Okay, things that we always like to tell students to take note is that velocity time graph, the gradient of the velocity time graph is actually equivalent to the acceleration. Okay, so when we are looking for acceleration, okay, we are actually looking at the gradient. Okay, we are actually asking for the gradient. So if you look at a velocity time graph for the section 1, okay, you'll find that the gradient of the line, if you look at the normal of the line, is actually getting steeper and steeper. So we are actually saying that the gradient for this section here is getting steeper and steeper, which means the gradient is actually getting bigger and bigger. The value of the gradient is getting bigger and bigger. And similarly, if you look at the gradient for the section 2, it's actually getting gentler and gentler, which means the gradient value is actually getting smaller and smaller. Okay, as for section C, you'll find that the gradient of this line is a horizontal straight line, which is what we commonly say the gradient of this line, horizontal line, is actually 0. Okay, and same thing, how do we factor in the math with the physics concept is we always remember that the impact of gradient on this graph is actually referring to the acceleration. So when we say that the acceleration of the gradient of the graph is actually increasing for section 1, we are actually saying that the acceleration, okay, is actually increasing. For section 2, if we comment that the gradient is decreasing, we are also indirectly inferring that the gradient of the acceleration of this object at this segment here is actually decreasing. Okay, so first one is increasing, second one is decreasing, and you find that if I comment that the gradient is 0, it will mean that the grade acceleration for this section here would be 0. Okay, because the gradient and the acceleration is actually tied together. So increase, decrease, and 0. So the only one that fits the answer will be increase, decrease, and 0, which is option A. Okay, so this is one aspect that we always like to tell students to actually to refresh or to revise. What do we mean by velocity time graph? Okay, to make use of the properties of the graphs, the gradient and the area under the graph, where these two segments actually represent the important information. Okay, now for question 3. Question 3 is a simple kinematics question, whereby we look at it as in terms of average speed. Okay, the calculation of average speed, the formula. Average speed, the formula will be total distance divided by the total time. Okay, the things that we want to be extra careful here is we know that the total distance is 5,000 meter, definitely. Okay, it's given in the question. The time taken here, take note, is 8 minutes 43 seconds, 8 minutes 45 seconds. So between A and B, the time taken actually for the travel, for time taken is actually what we know as your 2 minutes 40 seconds. Okay, so you take a look, this is 43, this is 45. So there's a difference of 2 minutes. Okay, then after that, how much time has passed? 17 seconds, it changed to 57 seconds. So total, we will have what we call 2 minutes and 40 seconds. But take note, 2 minutes and 40 seconds is not just like 2.4 or something like that. Okay, 2 minutes and 40 seconds, you must convert it to seconds. So 2 minutes is inherently 120 seconds and 40 seconds. Okay, so you will be adding another 40 seconds here. So the total time we are looking at here is actually 160 seconds. Okay, so if you know the time is 160 seconds, the distance traveled is 500,000 meter. Okay, you use the formula 5,000 divided by 1.6, you will have a nice number to be, I think, 31.25. When you round off to 3SF, it will be 31.3. Okay, I would say question 3 here, the trick that the marker lay on in this question is actually is on the conversion of time. Okay, to actually allow students to actually test students to see whether the students know 2 minutes 40 seconds is actually 160 seconds. Okay, maybe some students will have the urge to actually just use 2.4 seconds. Because 2 minutes 40 seconds. Okay. Question 4, 6 Newton, 8 Newton. Okay, they are given this question. This is what we know as your vector additions. Okay, we can use your parallelogram method. So what we do is we will produce this line, this force, copy and paste on the other end. Okay, so we will have actually two parallel lines, to form what we call a parallelogram. Okay, then after that, what we do is from the start point to the end point, you will have your resultant force, acting on the object. Okay, and with this picture here, you will know that the answer will be actually exactly the same as your option A. Okay, so what we are using here, we are actually using parallelogram method, for vector addition. Okay, so if you have not revised on your vector additions, parallelogram method, or tip-to-tail additions, you can actually refer to the video that I created for these two sections, for vector addition. Okay, I will leave the link in the description bar below and in the URL on the top right hand corner of the video here. So you should be able to see a link here, so you can actually click it. Okay, so just take note of it. Okay, somewhere here. Okay, so you can click on the link and you can revise on your vector additions. Question 5. Question 5 is an interesting one. Okay, question 5, you deal with dynamics, whereby you tell the students how the resultant force actually changes with time. Okay, then after that, the question actually go one step further to actually ask the students to deduce the speed time graph for the object here. Okay, so between resultant force T0 to T0, the resultant force is decreasing. So if you look at resultant force, F net equal to ma. Okay, based on the question, the resultant force is actually decreasing. Okay, so if the resultant force is decreasing and the object is always the same, is the same object, means I can safely say that the mass is actually constant. So if the resultant force is reducing, I can also make a comment to say that the resultant force is reducing, the acceleration will also be decreasing in the same direction. Okay, so which means effectively I can have actually a graph, okay, that denotes the acceleration changes with time. So between 0 to t naught, my acceleration will have the same trend as my resultant force, okay, followed by 0 here. So my acceleration will also be 0. So I can safely say that the acceleration of this object, okay, for 0 to time, for 0 to t naught, okay, let's look at the time 0 to t naught, okay, I can safely say that between this timing, my acceleration is definitely based on the graph is still positive number. The acceleration is actually decreasing. Okay, so these are the two factors that I can deduce from the graph. For t naught, beyond t naught, I can say that the acceleration is actually 0 and it always remains 0 for the rest of the time. So what we means that here, what we do is, what do I mean by how do I infer the speed time graph? Okay, here we have to take note is that when we say speed time graph, what can we deduce? How can we draw relationship between speed and acceleration? Is that for velocity time graph, the gradient of the velocity time graph actually give us information about the acceleration. So whatever the graph has, whatever velocity time graph have, okay, the gradient of the velocity time graph should actually tell us the shape of the acceleration. Okay, it should actually describe this shape. Okay, so let's look at which velocity time graph actually matches my acceleration time graph behavior. Okay, so now let's take a look for the first segment here. Okay, remember for the 0 to t naught, okay, 0 to t naught, the important thing is 0 to t naught, the acceleration is actually positive and it has to be decreasing. So let's look at which section of the graph that fits this description. Now for graph A, okay, you find that the gradient is actually a positive number, but the gradient is actually getting gentler and gentler. So what we can deduce from this area is that the gradient is actually positive and the gradient is actually decreasing. For graph B, you take a look. For graph B, the gradient is actually getting gentler and gentler and gentler, and it's actually a negative sloping line. So I can deduce that between 0 to t naught, this area, my gradient is actually negative. My gradient is actually getting gentler and gentler and gentler. So which means that the gradient is actually getting smaller and smaller and smaller. So if you do the same for the rest of the graph, where you find that actually graph A, okay, option A actually fits the acceleration description here. So that's why I can safely say that I can deduce that A is actually the answer. Okay, so this is what we mean by how we need students to actually make reference from the force time graph, make relationship to the acceleration time graph, and eventually make another inference to the speed time graph. Okay, it's like a 3 steps inference or what you call a 2 steps inference. Okay, so just take note of this. Okay, yeah, it is quite an interesting question. Okay, it requires the students to actually take description of the VT graph to another new level. Now let's look at question 6. Question 6 is a mass weight question, so I will not dwell too much. The formula, I will say it revolves using the standard formula. Weight is actually equal to mg. Okay, in this question here, the object is 15 kg. Okay, it's subjected to different gravitational field strength. Okay, and same thing like we always tell students is that mass by the definition is the amount of matter in the object. So regardless of location, whether it's on moon, at different part of the earth, as long as the object, the mass remains the amount of matter remains the same, actually mass remains constant. Okay, which I believe most of the students will actually are aware of this, because this is quite a common question that appear very often. Okay, so most likely you'll be able to deduce the answer straight away already. Okay, so from here I will not delve too much. If you need me to explain on this question, okay, just let me know, leave your comments, give me a feedback on the comment bar below. Okay, then after that I will get back to you ASAP. Now, question 7. Question 7 is an interesting but familiar question. Okay, I've seen it in other past year paper and even the O-level paper, if I'm not wrong. Okay, it requires the students to actually look at moments. Okay, to push the ball up, it requires a moment, and moments actually is force times distance. And this distance is what we call perpendicular distance. And I need the smallest force. a smallest force here, if I want the force to be small, okay, and to turn, okay, to rotate or push the ball up, I need a minimum amount of moment. So if my force is to be small, it will require the perpendicular distance to be as big as possible. Okay, so I'm basically the question, when the question is asking for a smallest force, is also indirectly asking me for like the which of the force will have actually the greatest or the longest perpendicular distance. Okay, pivot is here. I will say this pivot is x point x. Okay, same thing here. Okay, here the question tests on how the students actually deduce the perpendicular distance. Okay, so if you have forgotten how to use a perpendicular distance, I've done a video on how to identify perpendicular distance in under the under the topic turning effect. Okay, I'll leave the link to in the description bar below. Okay, on how to find a perpendicular distance. It is a technique. Okay, just once you know the technique, it's actually quite simple one. Okay, so now let's use that technique. Okay, so let's say example, I will be using the force A. Okay, so what I do is to find perpendicular distance. Okay, what I actually normally do is I will look at the force. Okay, I'll put line. So what we do is I will copy the force. I'll copy the line of action of the force. So the force is in this direction, vertical axis. So what I do is I just copy this line, and I will bring this line in the exact same orientation, copy and paste. I would say I will draw it at the pivot. So what we do now is I want the shortest distance between these two lines. Okay. So shortest distance, normally I tell students is actually you put a ruler between them, you should form an I or you should form a H with a shape lah. Okay. So the shortest distance between these two lines is actually a perpendicular distance. So this is what we call your D perpendicular for A. If I use force at A. Okay, so it will be like maybe like 80% of the diameter. Okay, so this is how I find the perpendicular distance of A. Is this the biggest? Okay, no. Okay, sad to say this is not the biggest. I would say this is the second biggest, I would say. Okay, so where do we find the biggest perpendicular distance? Is your option A. Yeah, sorry, option C. So, but let's look at how we find the perpendicular distance. Now, if we use option C, let's say option C, okay, option C, let's say I put my ruler at option C. Okay, the perpendicular distance is the line of action of the C. I copy. I will shift it to the pivot in the same exact orientation. Okay, I'll draw the line again. Then after that, what I do is I will find the shortest distance between them. Okay, that will be the perpendicular distance that I'm looking at. Okay, so the perpendicular distance is this shortest distance between them. It will be this line. Okay, which is exactly the diameter of the circle. Okay, of the sphere of the ball. Okay, so this will be the shortest perpendicular distance, what we call DC. Okay, and this in fact is actually the largest perpendicular distance. So that's why my answer for this, okay, I will place the force at C so that I can have a minimum force because the perpendicular distance is actually the largest. Question B, CG, center of gravity or center of mass, what some of us will call it. Okay, it's a point whereby all the mass are actually equally distributed. So based on A, B, C, D, I would say the nearest option for center of gravity will be at B, whereby the bottom segment of this mass, the total mass of this bottom section, is actually balanced out by the top section. Okay, so the two mass on top and above below the line is actually the same. That's what I mean by center of gravity. It's a point on the body whereby it actually distribute the mass of the object equally in all directions. Okay. Now, C, no, C, what am I saying? 9. Question 9. Okay, constant speed up the hill. Okay, constant speed up the hill. Okay, constant speed up the hill. If you look at this question, one look you'll know is dealing with energy, kinetic energy, gravitational potential energy. The clue that is given to us is the question say constant speed up the hill. The moment I say constant speed, what I'm actually telling you is actually the kinetic energy actually remain constant. Okay, so straight away you know your answer will be narrowed down to B and D. Okay, because it's constant kinetic energy. And as I go further up the hill, okay, this is the second clue, up the hill. Okay, the vertical distance is actually increasing. So which means my gravitational potential energy, MGH, actually will be increasing. That's why my answer will be D. Okay, so in the sense that even though there's no picture, okay, there's no numbers, no calculations, but actually the question has embedded two clues. Okay, the constant speed, which is tell us about kinetic energy. And the word up the hill. Up the hill implies the height is actually increasing. The embedded meaning here is we are looking at is the gravitational potential energy is actually increasing. Okay, so that's question 9. Question 10, okay, it's a standard definition, so I will not dwell too much. Okay. Number 11 is a classic example of power. Power will be energy divided by time. Okay, here take note, the time that we are looking at is actually in terms of seconds. Okay, so students, if you look at the timing, remember to change it to second and not just divide by 5. So we are looking at 5 minutes, or what we call 300 seconds. Okay, so the power that we are looking at, the timing is actually 300 seconds. Okay, so the power that I have is actually 10 watts. So this is 10 watts. Okay, energy, which is the numerator, is what I need to find. So I would say just simple calculations, simple algebra. So the total energy here we'll have for energy will be 300 times 10. It will be a simple 3000 joules. Answer D. Okay, so let's take note of it. Simple. Okay, booby trap that we use is always the same booby trap. Okay, timing. The time has to be in second. Okay, because for energy, the calculation, the formula has to be in SI unit. Okay. Question 12. Okay, evaporations. How does the object, how does the liquid, the molecules behave when evaporation actually take place? This is evaporation. Okay. Now, same thing, the escaping molecules. Okay, there is when you talk about evaporation, there are two segments, there are two sections that we're looking at. One is if we're looking at the escaping molecule, the molecule that's going to escape. Then after that, there's another segment we look at is the molecules that's remaining. Okay, and when you talk about evaporation, one of the highlights that we always talk about is we have this thing called cooling effect. Okay, because why? Because when the energetic molecules left the system, the remaining molecule, which is a lower kinetic energy, will actually have a lower temperature. So that's why for evaporation, okay, definitely the liquid temperature will be decreasing. So it's either A or C. And the escaping molecule who will escape is always the higher energy. The higher energy will be the one that is remaining. The higher energies are the ones that will escape, and the lower energy, okay, will be actually remaining in the liquid itself. Okay, so take note of what energy or which section the question is looking out for. But sometimes instead of escaping molecule, the question can ask like the remaining molecules. Okay, if it's asking for remaining molecules, the energy level will definitely be the low energy. Okay. Now for 13 is a freezing, melting, or what we call a heating craft. Okay. Melting point of the magic ice cube here, I will not dwell too much. It's a classic example of heating curve. So students should be well versed on which section the graph actually dictates a melting or dictates a boiling. Okay, so take note of the answer. Now, 4 pieces of matter. Okay, we talk about heat transfer, absorption, all these things, and conduction, evaporation, and radiation. And here, particularly, the question look for radiation. And when we talk about radiation, there are certain clues that we actually like to tell students to take note of. Okay, when we talk about radiation, we are talking about the temperature. We are comparing about the temperature of the objects versus the environment. We are looking at the surface of the object, whether it's rough, big, whether the surface is big or small, big surface area, small surface area. Okay, then after that, we look at the texture. Okay, the texture, whether it's dull or shiny. Then after that, we look at the color, whether it's black or white, okay, dark color or light color. Okay, these are what we mean by the clues that we need to take note when we tell students when dealing with the mode of transfer. Okay, there are more clues regarding the other two modes of heat transfer. So eventually when we talk about conduction, radiation, and convection, there are actually clues in the question to hint to students what are the possible mode of transfer. Okay, for the clues and for the keywords, okay, if you have forgotten, okay, I have a table, okay, that actually summarize most of the clues or the common clues that are available. Okay, I'll leave the link below in my description panel. Okay, and I also leave the link in the top left hand corner, okay, or sorry, the top right hand corner of your screen. Okay, that will be telling you where's the video that has the clues and keyword summary of them. Okay, so for radiations, okay, maybe once they absorb most radiation, we know black is definitely a best absorber. Okay, and we also know that for it, the best absorber, the texture we are looking at, it has to be dull, area has to be big. Okay, so it has to be dull area and dull. Okay, and reflect the most means what we call, okay, reflect the most or what we call absorb the less. Okay, so it's basically a poor absorber. So for a poor absorber, it has to always and anything to do with your color will be white. Texture definitely has to be shiny. Surface area maybe has to be small. Okay, so these are the clues that's given to us. So this is what we have deduced for me to absorb the most, reflect the most, or what we call absorb the least. Okay, when we say reflect the most, it also means indirectly I'm saying that the object actually absorb the least amount of thermal energy. Okay, so the only option that has all this is actually option B. Okay, so take note of the keywords, take note of the clues when we talking about different modes of heat transfer. Now for 15 is a standard example of the property of the waves, wavelength, amplitude, all this. So things to highlight is students at your current level, after doing all the revision, this will be considered the basic of waves. So I believe that every one of you should know this. Okay, so this will be actually the wavelength of the graph, where this will be known as the amplitude. So effectively, if you look at it, you will know that the answer is B straight away. Okay, I would say you can solve this within like 5 seconds. Okay, these are what I mean the basic of the waves topic. Okay, EN spectrum, I will not dwell too much also. EN spectrum, when you look at EN spectrum, where students, confirm you have to know the arrangement of the waves that we're looking at. Arrangement in terms of what? In terms of frequency, in terms of the wavelength of all the EM components. Okay, radio wave, gamma ray, X-ray, ultraviolet, visible light, infrared, all this, etc., etc. You need to know who is the largest wavelength, who has the highest frequencies, okay, and how they look like when I place them on the electromagnetic spectrum. And the other aspect we look at is with the users, okay, the users of gamma ray, the X-rays, or infrared and ultraviolet and all these components. Okay, then after that, there are one small section we look at is it could be looking at the harmful effect or disadvantages or the pro and cons, or what I call it the pro and cons of these waves. Okay, so students will have to know when we're talking about electromagnetic spectrum, what are the components, what are the users of the component, what are the advantages of using these components. Okay, so all these are like I would say it's facts, and students have to be fairly well versed in this area, especially the arrangements, the users, and pro and cons for all the components. Okay, so with that, if you have done your basic homework, okay, I would say this question 16 is a straightforward case. Now, for 17 is the clue given to you is when a negative charge rod is placed in between them. P is repelled, okay, Q is attracted. Okay, so definitely when we talk about attraction, when we talk about repulsion and attraction, it leads us to certain keywords that we always like to tell students. When we talk about attraction, we are looking at where? We're looking at opposite charge. Okay, and if we're looking at repulsion, we are looking at like charges. So these are the clues that's given to us. Okay, so these are the meaning. These are the meaning when we tell the students repel. When this is what I need the students to infer when I talk about attraction. So if Q is going to be attracted, and there is going to be opposite charge, so I can safely say that if this is my negative charge, okay, my Q will definitely be a positive charge because it has to be opposite charge for it to be attracted. And P is repel, it will definitely means that if my rod is a negative charge, for it to repel, it must also have a same charge, or it must have negatively charge. Okay, because light charge repel. Okay, and with this, I would say fairly straightforward. You will tell us that P has to be negative and Q has to be positive, which lead us to be option B. Okay, fairly straightforward, nothing complicated. Okay, which of the circuit the voltmeter reads 7.2? Okay, this is a simple example or simple, I would say a simple circuit or simple series circuit. So students will have to look at the basic. Okay, the way to look at it, there's only one way of doing it. The students have to look at the current that's flowing through the circuit. Okay, the total current that's flowing through the circuit. So if I know that, example, if I know the total resistance here is RT in series, so it'll be 5 plus 3. So it'll be a simple of 8 ohms. Okay, the total EMF or the total potential difference is the EMF, which is 12 volts. Okay. So if I use Ohm's law, VIR, okay, if I'm looking at total resistance, total voltage, potential difference, and total current, I can actually find that the current flowing in the circuit, okay, IT is actually 12 volts divided by 8 ohms. Okay, so 12 divided by 8, if you look at the calculator, it will be, okay, 1.5 amp. So this current here will be 1.5 amp. So if I have a current flowing 1.5 amp, I can actually use Ohm's law again on 3 ohm using V equal to IR. So V3 is equal to current times I3. If I want to look at the potential difference of the voltmeter at 5 ohm, I'll use Ohm's law again. So Ohm's law, V5 equal to IR, resistance 5, okay, which is 5 ohm. So you know that the current in both cases actually is the same number, which is your IT. Okay, which is your IT. Here, this is IT, this is IT. So from there, I will be able to work out the individual component, or to be exact, I should be able to work out the value of in my voltmeter. So if I do this for option A, B, C, D, I should be able to deduce the answer to be actually option B. Okay, option B, whereby voltage at 6, potential difference of 6 ohms across 6 ohm, current in the circuit across 6 ohm resistor. Okay, I should be able to get a 7.2 volts. Okay, for V6. Okay, so the current is the same thing, IT. Okay, so the effective, I would say this question is look at the basic of series circuit, whether the students know how to handle a series circuit, which the student must know how to handle, because this is very, very basic of your electrical component, electrical circuit. Okay. Now, question 19, it looks at resistance in terms of length, area, cross-sectional area, which will actually bring us to the basic formula of resistance, R equal to rho L over A. Okay, so effectively, we are looking at copper. Okay, so if I have the same copper wire, means the resistivity value is the same. So effectively, I'm saying that because we are using the same component, your resistance actually depends on L and your area. Okay, your L, let me rewrite this. It actually depends on your L and your area. Okay, so which means I'm saying that my resistance will increase when my length of the wire increases or the thickness of the cable decreases. Okay, so how much will I reduce? How much would the resistance change? For example, for resistance Y. Resistance Y, okay, the length actually has doubled. Okay, so which means my resistance will double at least minimally due to my length. Then after that, the cross-sectional area actually has half. Okay, has become smaller. So the smaller the cross-sectional area, the bigger is the resistance. So if I have half times, I reduce by half, my resistance value will actually multiply by 2. Okay, if you compare to the wire X. So effectively, my resistance because of these two changes actually becomes 4R. Okay, so that's why I can safely say that my resistance value for Y is actually 4 times of X, which is 4R. Okay, so look at how I use length and area to deduce how the formula for how the value of resistance actually works or change. Okay, last question 20. Question 20. This is what we mean by the rating of the kettle. Okay, 600 watts kettle. Okay, is a 240 volts, and there's this 700 cm cube. Most likely for kettle, it will be maybe the quantity, the amount of water that kettle can hold. So what is the normal current through the heating element? Oh, power. I have power, I have current, I have voltage. So the basic formula that I'm looking at will be power equal to I times V. Okay, so if I have the power of the kettle is 600 watts, potential difference is 240. I should be able to calculate the current of the kettles quite easily. So with this, if you look at your calculator, 600 divided by 240, my current here will be effectively 2.5. 600 divided by 240, it will be 2.5 M. Done. Okay, so just take note for this type of question. Usually, maybe if you're looking at structure question, maybe after looking at the normal current, which is 2.5, maybe the question will ask you to suggest a suitable fuse. Okay, the next best fuse that I'm looking for. So the possible next best fuse that I'll be using, it could be 3M fuse. Okay, so with this, we have come to the end of the paper 1, the first. Okay, now we look at question 1 of paper 2. Okay, question one here. Okay, it's a basic mass weight density topic. Okay, so what we are looking at the density of the rock, which is 5.5 gram per cm cube. The volume of the rock is 20 cm cube. So with these two information, we can actually use the density formula. Density equal to mass divided by volume. And here I would say with these two numbers, okay, I can actually deduce, or I can actually calculate the mass of the rock here. Okay, so I should be able to calculate the mass of the rock. Okay, the mass of the rock. Give me a minute here. Mass of the. Then after that, okay, then we can proceed to look at what the questions want us to look to calculate or to answer. Okay, what do we mean by gravitational field strength? Okay, here, here I also like to highlight to you again. Okay, when we look for definition, when we are asking for definition of the certain terms, okay, certain concept. Okay, here take note in the textbook there is general definitions. Example like gravitational field strength. The general definition will be like force acting on a unit mass of object. Okay, that will be a standard definition. But in the paper that you always see more often when we ask for definition, we will be asking for definition, but we do not want the generic definition. For example, right, when we ask for to define gravitational field strength, I will actually pack like context will be 1.6 Newton per kg. So the definition or the answer for this question I'm looking for is I'm not looking for the generic definition, force per unit mass acting on the object for gravitational field strength, but rather that I will actually want the definition of the term, but with respect to the question. For example, force per unit mass. So I'm looking at the mass is 1 kg, and the force I'm looking for is now I have to write it down explicitly to say it's actually 1.6 Newton per kg acting on the object. So this is when we talk about definition in this, I would say in this context, in this era, most of the time we will not be asking for the generic one. We will actually be asking for the generic one plus a bit of modification so that the definition is in context with the question. Okay, so that's what we mean by your, I would say your current way of defining. Okay, so remember for students, if you write down the generic definition, remember to tweak a bit, okay, so that you answer the question with context. Okay, so the important is the context of your definition, not just copy and paste the generic definition. Okay, the mass of the object I mentioned before already, so this one I will not dwell too much. The formula is actually here. Okay, the working weight of the object. Okay, weight of the moon. Okay, standard formula mg. Okay, the only difference here is the question is asking for moon. So the gravitational field strength of moon, it has to be 1.6 Newton per kg, and this gravitational field strength is given in the question. So choose the correct field strength. Okay, don't just blindly use 10 Newton per kg. Okay, so take note of the question, read the question. Okay. Now the astronaut shoot the rock sideway on Earth and on Moon. Okay, the context is shoot, and he shake it, and after that, why is it equally difficult, okay, to make the action? Here we are not talking about whether is it how fast the moon, the object can accelerate on Moon or can accelerate on Earth. Okay, what we are looking at is before that slight acceleration, how the ease of shaking it, whether is it easy to shake the rod or is it hard to shake the rod. Okay, that action. Okay, so when we talk about that particular instances, we are actually looking for the context, or we are looking for the students to be applying the concept of inertia on the object. And we look at inertia, we are actually looking at the mass. Okay, and of course, okay, when we look at inertia, okay, we are using the concept of inertia. We are actually looking for the students to use the word, okay, mass, because these two are related, and we are also looking at the students to use like keywords like reluctancy, okay, reluctancy to change motion. These are what we call the keywords, okay, to change motion, okay. So in your answer, okay, the students need to highlight all these keywords. So that's why for this question, the astronaut mentioned that it's actually both equally easy or both equally difficult to shake the rod. Why? Because the inertia of the rod is actually the same. Why? Because the mass of the rod is actually the same. So, and thus, okay, if you want to continue, you can say, and thus, both rod has the same reluctancy to change motion. Okay, so if you write in this way, you'll find that it's quite comprehensive. I would say that most of the time, whenever the questions need the students to apply inertial question, usually the answer will actually encompass these three keywords. Okay, mass of the object, pack it to inertia, and explain what happened using the word reluctancy to change motion. Okay, this is what we mean by the standard keywords that we always try to embed inside the answer. Question 2, velocity time graph. Okay, it's a classic example. Okay, it's just that maybe we are looking at the graph here is like there's a slight different normal graph versus other questions. Normal question we're looking at maybe is more on the positive side. But in this case, there's this upside down or this negative segment here. Okay, it's slightly different. Let's take a look. Now the object is traveling from B to C at is 3 meters per second squared. There's acceleration. This is B to C. Okay, B to C. When we say acceleration for B to C, when I'm looking at it, velocity time graph, I'm actually referring to the gradient of the graph at BC. Okay, it's 3. Okay, so this is what the question tries to tell you. And similarly, when we talk about acceleration, there's a formula. Okay, final minus initial divided by delta time. Okay, so here we're looking for is just apply the formula. I don't think that it should be difficult. Okay, I think students should be, I would say 100% of you should be actually able to solve this quite easily. Okay, then after that, some phrases to describe the motion. Okay, when we talk about motion, we are looking at the acceleration. So here I will leave the answer to you. Okay, for example, when you're looking at AB, okay, so AB is a horizontal straight line. Horizontal straight line here, the acceleration here is actually, the gradient here is actually 0. Okay, or what we call the acceleration of the object is 0. Okay, and because it has 0 speed here, so this acceleration, although it's 0, it doesn't mean constant velocity, because the constant, before you look at, if you look at the motion of the object at this instant is actually the speed is 0 meter per second. So what we are looking at is not traveling at constant speed, it's actually what we call stationary. Okay, so AB, the answer should be stationary. BC is a constant gradient, or we call constant velocity, constant acceleration, or what we call a uniform acceleration. Okay, so similarly, okay, description on the graph, like I mentioned in my previous video in chapter 2, okay, when you talk about description, it's always about describing the graph in terms of accelerations. Okay, in describing the gradient of the graph in terms of acceleration. If you have forgotten about it, okay, you might want to look at my video in chapter 2. Okay, I typed the link, I left the link below there regarding chapter 2 description of the graph. Okay, you might want to just refresh it if you have not gotten to that section during your revision timing. So C and D, I'll leave it to you. It's quite I would say it's quite straightforward. Okay, state one similarities and differences between the motion at BC and FG. So where is BC and FG? BC is upward sloping, and FG, okay? FG, okay? Take note. Constant thing, I would say the similarity could be that both are constant gradient, okay? But one thing about this gradient is you can take a look. The BC is what we call a positive gradient. Okay, your EF, EG, okay, is a negative gradient. Take note of it. It's a negative gradient. So there is slight differences between them, negative gradient and positive gradient. But similarity between them is that they are constant. Okay, it's a fixed number. It's not changing. Okay, so that's what I mean by both are both are fixed value. Okay, but one is positive, one is negative. Okay, so the differences between them, if you look at the motion of the object, is like the whole motion actually revolves like the object is actually accelerating, getting faster and faster. Then after that, he travel at constant speed. Then after that, he start to slow down. So that's what DE is trying to describe to you the motion. So where he's slowing down at E, where the object will be completely slow, it will completely stop. EF will be stationary. Okay. Then after that, FG, you will find that FG, the speed is increasing, but it's in the negative area. Okay, here I would say that the negative region here, it implies, okay, in opposite direction. The negative sign here revolve opposite direction. That's what the negative velocity means. Okay, that's what the negative velocity means. Okay, the negative velocity actually denotes the object is going in the opposite direction. Okay, so that's why I can safely say that FG, okay, and BC, although they are constant gradient, they are accelerating. Okay, but both of them actually takes different direction. Okay, plus and minus. Okay, so FG actually involve opposite direction. That's why I can safely say the difference between them is opposite direction. Okay, so how do I deduce? Same thing is how do I deduce that is opposite direction? Okay, so refer to the explanation I given you before. Okay, I trace out the motion for the entire object ranging from 5 seconds all the way until 55 or 45 seconds. 45 seconds, yeah. Okay, so I trace the motion to see how the object behaves. Okay, accelerate, constant speed, slow down. Then after that, he stopped for a while. Then after that, before moving off again in the opposite direction. Now for question three is forces. Okay, it has a graph here also. Okay, with a resistive graph. In this case, resistive graph is referring to this left hand side, this left graph, left forces. Okay, excuse me. Now the acceleration of the object at 4 seconds. Now acceleration of object at 4 seconds. Take note for this object. Okay, there is two forces acting on it. So if you look at the Newton force, F net equal ma. There are two forces applying on it. Okay, so it will be the what we call the forward driving force minus the resistive force. Okay, so you ma, so it will be indirectly, I'm saying it will be 1,500 minus the resistive force based on the graph. Then we have a m and a. Okay, is the mass given? Yes, the mass is given 1,008. So I can actually replace it with 1,008. Okay, the mass of the object. Okay, so this is what I'm looking at. So based on the question, this is, I would say, the equation that I can derive straight away. Now, so based on the question, what is the acceleration on the graph at 4 seconds? At 4 seconds, let's take a look at 4 seconds. Okay, the 4 second, the resistive force, Fr, is actually 1,000 Newton. So effectively, if you look at these equations, okay, the resultant force is actually 1,500 minus 1,000, which is the resultant force. You get 500. After that, you sub inside the equation, substitute inside the equation, you find the acceleration of the object to be 0.28 meter per second squared. Okay, quite easily done. Now, same thing is with calculations. Okay, how does the resultant force at 2 seconds and 6 seconds behave? Same thing. Okay, repeat. It's the same. I would say it's the same as part question 2. It's just that now you look at two timing. First timing I'm looking at is 2 seconds. 2 seconds is here. The resistive force I'm looking at is 500. The second timing I'm looking at, so let's say I write it down first before I forgot. Okay, so the resistive force here is actually 500 Newton. Okay, at 6 seconds, 6 seconds is here. 6 seconds is here. Resistive force is 1,500. Okay, so this is 6 seconds. So the resistive force is 1,500 seconds. 1,500 Newton. Okay, and then what I do now is I will just repeat what I did in question A. I'll use this formula. Okay, the resultant force, Newton's law. I will apply directly to your part B. Right, like what I did here. Okay, I'll look at it in terms of the resultant force, and from there I can deduce the accelerations. So from example at 2 seconds, I can deduce the net force is 1,008. 1,000 is 1,000 Newton. And given that the mass is 1,008 kg, the mass given is 1,800 kg, I can actually deduce the respective acceleration. Okay, same thing is at 6 seconds, the resultant force is 0. Okay, it will mean that the acceleration at 6 seconds here is actually 0 meter per second square, or what we call constant speed. Okay, so these are the information that is actually embedded inside the calculations. Remember, the calculations and explanation, they are not separate issues. They actually work hand in hand. They actually complement each other. With my calculations, with your calculations, okay, you can actually deduce what is the behavior of the acceleration of the objects, and indirectly deduce the behavior of the object here. Again, which is what the question is actually trying to tell you. Okay, so what we are looking at is, what I actually encourage students to do is, don't just look at calculation as calculations. Calculation and explanation and keywords, they are actually all together. They complement each other. Where the calculations, the formulas actually serve as a guide to tell students what are the keywords, what are the phrases that I need to include in my answers or in my explanations to make it clear or make it precise for the marker to see, to understand. Question 4. Okay. Question 4 is I would say it's a basic question. Okay. The object going up the slope. Okay. Speed is 2 meters per second. Okay. And yeah, the first few is A and B, talk about the standard definitions. Okay. So I will not dwell too much. Okay. Students, you need, remember, for this A and B is generic definition. So you can just copy and paste the definition that it has in the notes, in the textbook. Okay, and just paste it here. What is the maximum vertical height that have reached by the block? Okay, here I would say it's a standard example of conservation of energy, whereby the energy at the beginning will be EK. It will be converted totally to EP, which is your gravitational potential energy. So whatever energy I have at kinetic energy will be given to potential energy. It will be transformed to potential energy. So formula for kinetic energy is half mv squared. Formula for MGH, for gravitational potential energy is MGH. So you equate them together, you get the height to be 0.2 meter. Okay, easily done. Question 5, your thermal property. Now, for thermal property, for combined science, okay, generally for thermal property, it involves explanations, and there's actually keywords for each of them. Okay, for thermal property, the concept that we're looking at, we are focusing on the internal energy of the object, the internal energy of the molecules. And when we talk about internal energy, we are actually looking at two aspects, which is the internal kinetic energy and the internal potential energy. Okay, and internal kinetic energy, like we have mentioned in the topic, okay, in this topic, kinetic energy actually tell us is pegged directly to the velocity of the object and indirectly pegged to the temperature of the molecules or of the object. Gravitational potential energy, what it tell us, what's the impact on it on the object, is actually regarding the change in state. So at each different section, when we're talking about heating, boiling, freezing, okay, whether it's heating from solid or heating a liquid, okay, we are looking at the internal energy, we are looking at the kinetic energy and the potential energy of each of the object at each stage. And at each stage, the kinetic energy, the potential energy will change differently. Okay, but there is quite a standard process, because at heating phase, or what we call stage 1 here, the melting phase, stage 2, okay, then after that it can be heating phase again, and what we call eventually a boiling phase. Okay, at each of these stage 1, 2, 3, 4, okay, the kinetic energy and the potential energy would behave differently. Okay, although it's different, but the behavior is actually quite predictable. So that's why when I went through this topic in chapter 10, I think chapter 10 or chapter 9, okay, internal energy, okay, I actually gone through in details what are the energy changes you have at each of the stages. Okay, if you have forgotten or you have not revised until then, okay, I leave the link for for thermal property, the keywords for this heating graph, cooling curve, heating graph, all this in the description link below. Okay, we refer to it. Okay, just do a short refresher course. And if you have done it, okay, then we'll look at answers at the 5A and 5B to see whether have you wrote all the necessary keywords, okay, to illustrate the behavior. For example, VW and XY. VW and XY, the heating phase, stage 1 and stage 3. Okay, we will compare what are the what are the forces of attraction, okay, and what's the arrangement of the molecules. Okay, this is, I would say, the arrangement. Before we talk about arrangement, before we talk about the forces of attraction, we have to always remember at VW, what I call stage 1, the object is actually is a solid here. Then after that, stage 2, WX is what we call a melting phase. Then after that, XY is still a heating phase, so it's a liquid already. Okay, so this is what we call heating. Stage 1 is a heating. Then after that, stage 4 is what we call a boiling stage. Okay, so when we talk about VW and XY, we are actually looking at it as a heating of a solid. XY is actually heating of a liquid. So in terms of VW, is a orderly manner. Arrangement will be an orderly manner. Why? Because it is a solid state. Particle is arranged in orderly manner. Okay, XY is always, if it's liquid state, is always in the disorderly manner, or what we call XY. They are arranged such that they can actually slide over each other. Same thing, forces of attraction. For solid, it will definitely be stronger than the liquid state. I would say it's quite straightforward. Okay, so nothing fanciful here. Okay, then after that, we look at what happened to the segment WX. WX here, we refer to melting. When we refer to melting, when we talk about melting, describing the energy change in melting, we are actually need the student to describe what happened to the EK and what happened to the potential energy. Okay, so if you've done it, you know the keywords, you should be looking at it, you should be writing in a way that, okay, where you should encompass potential energy and you should be encompassing the answer to include kinetic energy. And we talk about your potential energy. Okay, we talk about your potential energy. You should be looking at, okay, potential energy. Okay, so normally what we look at, when I tell students, when we look at potential energy, okay, we will actually be telling the students to actually include, okay, the change in phase, change of states, or what we call your changes in your intermolecular bonds. So normally we will actually encourage students to write it in this way. Okay, so the first segment will be actually to use it to break intermolecular bonds or to weaken the intermolecular bonds, okay, or intermolecular forces of attraction. Okay, then after that, what we do is we actually tell the students to encourage students to actually tell the marker to say there is actually a change in state. Okay, from solid to liquid. Okay, so we always encourage students to actually write these two phases when we're talking about the potential energy changes in the intermolecular forces and actually talk about state change. Then after that, we talk about kinetic energy, we always pack it to no change in kinetic energy at this stage, WX, because why? All the energy has been diverted to your potential energy. And because no change in kinetic energy, the temperature always remain constant. So you look at the phrasing for keywords, if we talk about kinetic energy, it's always talking about kinetic energy after that ending off with the temperature. Okay, so this is what I mean by the tagging keywords. When we're talking about kinetic energy, you always tag it to temperature. Okay, so this is what I mean by the tagging keywords. Okay, when you look at potential energy, you're looking at the intermolecular forces and the state change. Okay, then after that, the C is a small calculation. Okay, the energy needed for WX. Okay, energy given. Okay, there's a 10 volts here, 10 watts here, power. Okay, and power is basic formula you're looking at is power is energy divided by time, or what we call energy is power times time. Okay, so given in the question, the time taken is from 1.5, okay, 0.5 minute to 1.1 minute. Okay, remember our time here has to be in SI unit. The time for the SI unit for time has to be in seconds. So that's why there's a multiply by 60, convert the minutes to seconds. Okay, then after you'll get the answer straight away. Okay, so in terms of calculation, I would say it's quite straightforward. Okay, in terms of explanation, okay, take note of explanation in B. Okay, I can ask you to explain what happened to the energy in the 4 stages, whether it's VW, WX, XY, or even YZ or onwards. Okay, so take note of the explanation, take note of what are the keywords. Okay, if you have forgotten, I repeat again. I have left the keywords, the link, the video for the keywords, okay, in the description panel below. Okay, you can go and click on it and go and take a look and to check that you have covered all bases regarding this topic, regarding this explanation for heating process. Light ray, okay. Light ray, okay. I would say this light ray wise, okay. Take note for light ray, okay. For light ray, take note we can only draw the 3 standard light rays with the 3 light ray with all the 3 behavior. Okay, so for example, your ray, this particular ray here, it will be the last ray that you want to draw, because I will not know where this ray actually move. Okay, whether does the ray converge here, or does the ray converge here, or does ray converge even further. So I will not be able to know until I actually know the location of the object. Because for light ray, I only know the motion or the movement of the light ray, okay, for 3 standard positions. Okay, so namely the first ray, which is from the object all the way down to the optical center. I will know how this light ray behave. I will also know the light ray, which is a parallel to the principal axis. After passing through a lens, I will know where it's going to behave. Okay, so if you look at the working, okay, the first ray I will draw will be this straight ray. Okay, the ray, I will call this ray number 1. You pass through the from the object, pass through optical center of the lens, go straight through to the opposite side of the lens. Same thing, ray 1, this is what I call ray 1. Ray 2, okay, is parallel to the principal axis, and I will actually know that you will cut the focal length, focal point, and after that you go straight. So I actually know the behavior of the second ray. So these 2 ray, with these 2 ray, I will be able to find an intersection point, and that intersection point will indicate where the image is. Okay, and with that, I actually locate the image, and once I locate the image, I will actually know where this ray go to, okay, where this ray bend, how much this ray bend, how much this ray converge, because I know that this ray will definitely converge and it will definitely hit where the image is. Okay, so if you look at ray 3, ray 3 is the last ray that I will draw. Okay, because ray 3, there is no space. I will not know where is the angle whereby the ray will converge. I will only know the angles, how the ray converge, after I locate the image. Okay, so this is how I complete the ray diagram. This is how the ray diagram of the complete image looks like. Okay, so ray diagram wise, okay, if I have a video on the how to draw a ray diagram. If you have not revised on this section, same thing. Okay, you can click, I leave the link below. Okay, you can take a look at it. Same thing for ray diagrams. There are 6 ray diagrams. Okay, you have to know what are the 6 diagrams. So there are 6 of them. Okay, so 6 of them, you need to know them and know how to draw, and you need to know the locations of the objects. You need to know the location of the image. You need to know the characteristic of the image. If not, you will not be able to identify or to describe the image correctly. And after that, the last segment is for the 6 diagram. You need to know the uses of these lenses. Okay, for example, if I have a take note of the ray drawing, there will be one particular location whereby the object is less than the focal length. The moment is less than the focal length, based on the picture, I will know that it will definitely be a virtual image. And the image form will actually be magnified. Okay, and it will also be on the same side as the object. Okay, so this information actually I got it from, not from drawing, but actually not from the ray drawing that I've drawn somewhere, but actually I got it from the textbook or from the notes, whereby it's a standard outcome. Okay, so in this case, to get the answer for B, okay, I actually don't need to draw the ray myself. I actually know the answer because I actually take a note of the possible 6 diagrams and possible properties of the ray of the object and the image. So that's why I know that the answer will be virtual and it cannot be caught on the screen. I will also know that the virtual image will also be magnified. Okay, so that's why it's important to actually know the 6 diagram. ES spectrum, I will not dwell too much. Same thing as MCQ, you need to know the arrangement, you need to know the users, and you also need to know the properties of the ES spectrums. Okay. Question 8 is a classic example of sound wave. Okay, sound wave. Okay, from the look, you will know that if you look at the arrangement, you will find that the dots will actually be compressing towards the center, or what we call your particle tree. This particle tree will be actually the center of your compression. Okay, so this is where my compression is. Because how do I know it is a compression? Because you look at the rate, you look at particle 1, 2, and 4, 5. It looks like they are actually compressing to the center. Okay, towards particle 3. Okay, so just take note of the arrangement. So here what we are looking at is you have to analyze the dot, the movement of the dot. So 1 and 2 will actually be going nearer to 3. Particle 4, 5 will be actually going nearer to the particle 3. So 1, 2, 4, 5, if you look at the motion together, they will be looking like they are compressing on 3. So particle 3 will be what we call the center of compression. And same thing, you look at 11. 11 will be the center of compression. Also, if you look at particle 11, okay, why? Because 9, 10, and 12, 13, they look like as if they are compressing towards particle 11, which is what we call the center of compression. And after that, the reverse will be true. You look at 7, okay, 7 is what we call the center of refraction, okay, because the particle 5, 6, 8, 9, it looks like the particle is going actually further and further away. So it looks like as if 7 is being stretched on the left side and stretched on the right side. Okay, so that's what I mean by the center of refraction. B, definition, I will not dwell too much. Okay, so know your definitions. Okay, you have to know your definition. Okay. Question 9. Question 9 is a electrostatic question. Okay, static electricity question. So you're looking at light charge repel and unlight charge attracts. Okay, so the basic question, based on the question is how the plastic become negatively charged, sorry, how the cloth become positive charge. Now, same thing like I mentioned to my students. Okay, when we talk about charge movement, we always remember it's always the electron that is moving, because electron being on the outer shell, being smaller size, they will be actually the most easily being knocked out from their molecular structure, and from there you will start a series of losing electrons or gaining electrons. Okay, so the context that we are looking at is we actually need the student to look at the losing of charges. What charges we are looking at? Negative charges. Okay, so if I lose charges, I will actually become positively charged. If I gain extra charges, what charges? Negative charges. I will be negatively charged. So based on the question, okay, if I'm saying that, if based on the question, okay, if it's negatively charged, plastic is negatively charged, it will means that, okay, the plastic actually pick up electrons. Okay, and where does the particle pick up the electrons? Okay, because, okay, the cloth loses that electrons. Okay, and as a result, okay, the electron is picked up by the cloth. Okay, the electron is picked up by the plastic, and because the cloth loses electrons, the plastic become positively charged. The electrons is gained by the plastic rods, and as a result, the plastic will become negatively charged. Okay, so this is what we mean by your description of the keywords when we talk about charging. Okay, how whether you are positively charged or negatively charged, I will actually require the students to tell me where has the electrons moved to, and where does the electron come from. Okay, so by telling me who loses the electrons, I will be able to deduce that who actually become positively charged or who become negatively charged. Okay. So that's why the answer, I would say, is quite a standard set of, there's a logical process in the answer. Okay, explain why the matter in the hand will not be charged. Okay, now same thing, matter is what we call conductor. Okay, conductor. Okay, why is it a conductor? Because when we say it's a conductor, it means the electrons can actually move freely in conductor. And how do we mean by freely? Okay, it can move freely such that it can actually move to the ground. Okay, so it can move to the ground, and the electrons can move, it can flow down from the metal objects down to the ground, or what we call, it can be earth. So any excess electrons that I pick up, it will actually pass down to the ground. It will be what we call discharged straight away. So as a result, okay, the metal rod will not be charged. Okay, because all the charges on the electrons will actually be flowing out of the, maybe out of the metal bar already. Question 10. Question 10 is an example of your circuit. It consists of 3 resistors. Now take note, I would say the tricks that the marker is trying to tell students, okay, to trick students, is the arrangement of the voltmeter. The voltmeter look like I have a set of parallel arrangements, okay, but actually it's not. Actually 4 ohms are actually in parallel, 2 ohms is actually in series. The arrangement will look like this. Okay, if you redraw it, to be clear, it will be the battery, the cell, the 4 ohm resistor, the 4 ohm resistor is actually in series with the 2 ohm resistor. There's only a 2 ohm resistor. Okay, so the voltmeter is actually across the 2 ohm resistor. So this is where the voltmeter is. This is where the voltmeter is. Okay, so effectively the voltmeter doesn't affect this. Okay, it just measure the potential difference across the 2 ohm. So if you look at the arrangement of the resistors, okay, it actually consists of a parallel arrangement, 4 ohm in parallel with 4 ohms, followed by, okay, the R parallel, okay, okay, in series with the 2 ohm resistor, in series with the 2 ohm resistance. Okay, so this is R parallel in series with the 2 ohm resistor. Okay, so it's not that there isn't 2 parallel circuit here. There's only 1 parallel circuit, okay, which is in series with the 2 ohm. Right, so that's why if you look at effective resistance, it's actually the R parallel. This is actually the R resistance, which is R parallel. You look at the formula, then followed by in series with the 2 ohm. So you just add them together. Okay, so take note of the arrangement, take note of the circuit arrangement. You don't get tricked. It's actually one pair of parallel circuit only. One pair of parallel resistance only, not 2 pair. The voltage across 2 ohm. Okay, the voltage across 2 ohm. Okay, now the voltage across 2 ohm is that since we already have the total current, which is here, this current here, I can actually find the current. Okay, because why? I know that because from the battery, okay, the current coming out, the IT coming out from the circuit, from the battery, it go to the parallel branch and it will actually enter the 2 ohm. You actually enter the 2 ohm. Okay, the same IT will actually travel through the 2 ohm resistor. So effectively, if I want to look at potential difference across V2, 2 ohm, I literally need to know the current flowing through 2 ohm resistor. I need to know the resistance of 2 ohm, which is 2 lah. Okay, but indirectly, if I'm looking at this, okay, I also know that the 2 ohm, the current flowing through 2 ohm is also what we call the current flowing through the whole entire circuit, which is IT. Right, so effectively, I can actually calculate IT first. Why? Because I actually know the total resistance in the circuit, which is part A. I also know the total EMF or total potential difference in the entire circuit, which is the EMF of the battery. Okay, so with this, I can actually calculate the current IT. IT will be VT divided by RT. Which is 12 divided by 4, which is 3 ohm. So once I know 3M, once I know this is 3M, I can substitute 3M into the equation, which is I2. Okay, 2 ohm here. This is 2 ohm resistor. So I will get the working to be 3 times 2, and I will get the potential difference across 2 ohm resistance to be 6 volts. Okay, and so this is how I calculate the potential difference across the 2 ohm. In this question here, it looks like a simple question. It's a simple question, but actually it requires the students to do a 2-step working, not just 1 step and the answer will appear. No, it's actually a 2-step process. So the thinking process behind it is that the student need to work out that the current, the overall current in the circuit is actually equivalent to the current flowing through the 2 ohm. Then after that, the students have to work out the total resistance, total current. Then after that, bring it forward to calculate the current, the potential difference across the 2 ohms. So it's like a 2-step process. Current flowing through one of the 4 ohm resistors. Of course, if I know the current flowing through, the current here is 3 M. Okay, it's 3 M. And I know that the current will split. Okay, and how I know you'll split exactly half. Because the parallel arrangement, the 2 resistors are the same value. So the current will actually travel up and down equally. So that's why I will just divide so the current in each branch will actually be 1.5 M. Okay, so now this is the section A. So now we look at section B. Section B, there are 3 questions. You are required to choose 2 questions. So choose the correct question first. Remember to read all the 3 questions first. Okay, so now, okay, the question, first question, question 11, okay, which is on the ray diagram, okay, or it's more on the lenses, okay. Same thing, okay, you talk about the first segment here on these lessons, it bring us to refraction first, okay, the clue, based on the context of the question, okay, longer wavelength is refracted less than the shorter wavelength, okay. So blue is refracted here, so you are using blue first. Blue is refracted at, okay, so its focus is being converged to this particular point. So the question talk about how is light ray being refracted at the air and glass boundary. Air and glass boundary means from air to glass, so it refers to actually to this side of the lens. Okay, the left side of the lens. Okay, so the left side of the lens, this is what we call the air. This is what I call the glass. So the air glass boundary refer to this left side here. Okay, so air is less dense, glass is dense. So this is the context we are looking at. And same thing, when we talk about refraction, we talk about describing refraction, we always tell students to actually to cover in their explanation to cover the bending, whether it's bend towards normal or bend away from normal, depending on context. And we also tell students to actually talk about the change in speed. Okay, so we always tell the students to actually include these 2 keywords inside the speed when the question requires them to describe what happened to the refraction. Okay, so same thing, this is what we mean by it bends towards the normal. Okay, because it's traveling from less than to dense. And why this bends towards the normal? Because the speed of the lens, the speed of the ray, speed of the light ray or blue light actually slow down when it enters the glass. Okay, so because of these changes in speed, it leads to a change in direction. What direction? Bend towards normal. So that's why if you answer, we always include these 2 keywords. Okay, same thing, red light. Okay, red light, how we converge? Okay, so here you must know, here based on the question is red, longer wavelength will refract less. Okay, longer wavelength. So in this context, if you look at EM spectrum, students, you need to know the red light, whether it's a longer wavelength or shorter wavelength before you can conclude answer. Okay, so so here you remember, okay, based on the question, okay, your red light, if you look at the electromagnetic spectrum, red light actually have a longer wavelength. Okay, and because it's a longer wavelength, I know that you will converge further. Okay, after passing, it will converge less. Okay, so that's why I will deduce whether it converge more or less. Okay, because I do know that I have done my homework, I actually know that the red light has a longer wavelength as compared to the blue light. Okay, based on the electromagnetic spectrum. Okay, so take note of the context that the student need to know. The question is assuming. Okay, so for EM spectrum, it's a simple topic, but it's not a topic that because it's simple, then we tend to just ignore it. Okay, it's actually an important topic. Now, for the next part B, okay, you have the arrangement of the lens. Okay, the blue object, the lens is 10 cm away. Okay, and the lens, the focal length of the lens given is 5 cm. You are given 10 cm. Take a look, this is 10 cm. Focal length is 5 cm. So this will be actually 10 cm is actually 2f. Further away is actually 2f. Okay, 2f. This distance is actually 2f. Focal length is f, 5 cm. So this is 2f. Okay, so 2f, the moment I say 2f, so which means the object is at 2f. So if you look at the ray diagrams that we have in the textbook, you will know that 2f, okay, you have certain behavior. For example, I will know that 2f, the image will be the same size. The image will be real. Okay, it will be same size. Okay, so these are the property of the image, okay, based on the location. And where do I get them? It's based on the ray diagrams that I have in the textbook that I actually taken note of. Okay, and true enough, okay, and the question will ask, okay, if it's at 10 cm, what is the property of the image? So I will know, okay, it's like I mentioned before, it's real, inverted, and it's the same size. Okay, so without drawing any drawing, okay, I actually know the answer straight away because I have taken note of the properties of the object, these properties of the image at various positions, okay, based on the 6 diagram. Now, without moving the screen and the lens, without moving the screen and the lens, basically I move the object. Okay, so basically I move the object. Describe how will you move the object to produce a image, okay, a smaller size, okay, smaller size. So when I want the image to be smaller size, okay, to be diminished, okay, when I want it to be a diminished, based on the 6 diagram that I've taken note, there's only one case. The object distance must be more than 2f. Must be more than 2f. So which means I'm now at 2f. So for me to be more than 2f, I must move the object further away from the lens. Okay, that's how I get the answer. Okay, so take note of the answers and take note of how I deduce the answer. Okay, so the idea of the thinking process behind is actually more important. Okay, so it all started with the 6 diagram, paying attention to the 6 diagram. Okay, part C is deal with the calculations. Okay, calculation of ray diagram. Okay, to be exact, is refraction. And refraction, we have the formula sine. Okay, here the formula right here again, it will be the sine angle in the less dense medium divided by sine angle in the dense medium. Okay, remember less dense medium and the dense medium. This one, I would say most student, I would say 100% of students know where is the less dense, where is the dense, definitely. Okay, but important thing is remember the ray diagram. Okay, the angles that we're looking at from the ray diagram is always measured from where? It's always measured from the normal to the ray itself. So these 2 angles is the one that I'm concerned. It's always from the normal to the ray diagram, where it's not 40 degree or 30 degree. It's always measured from the normal to the ray, normal to the ray. Okay, so take note of the angles that I need. And same thing, I know that based on the picture, okay, from M to air, okay, based on the picture, okay, I actually bend away from normal. Okay, so based on the picture, I bend away from normal. So indirectly, if I bend away from normal, this particular medium, it will means that, okay, my M has to be a denser medium. Because when I travel from dense to less dense, then my ray will bend away from the normal. So indirectly, I will know that angle 50 is actually at the denominator. Okay, so this is how I deduce the angles. So knowing where the angle is and it's not good enough, you still need to know how the rays behave. Okay, from there, these 2 things coupled together, then you'll be able to deduce which angle is at the numerator, which angle is at the denominator. Okay, then after that, the question proceed on to calculating the critical angles, etc. Will not dwell too much. It's just, I would say it's a standard answer. It's standard working. Now, based on the question is now I have the ray diagram now. I change from 50 degree, I change to 70 degree. Okay, given that the refracting index, the critical angle is 62.2. Now, the moment the question tell you to find critical angle, when the moment I see the question telling me to find critical angle, I will in my head, I will actually take note of, maybe total internal reflection is coming. Maybe I will need to check what are the internal, what is the condition for internal reflection. So I will get ready. And true enough, the question asks, what happened if my angle I now is 70 degree? Okay. And based on the question, angle C or critical angle is 62.2. And double check for the total internal reflection, I need two conditions. I need angle I, okay, to be more than angle C. That's the first condition. Okay, not the only condition. The first condition is this. And the second condition I need is I need to make sure the ray travel from dense to less dense medium. Only when I have these two conditions satisfied, then total internal reflection will occur. Okay, look at how I look at total internal reflection. I'm not just looking at condition one. I have to take note that other than condition one, there is actually a second condition. Only when these two conditions take place, then my total internal reflection will occur. Okay, so after that, okay, once you have this in head, you actually be able to answer the question already. Okay, so take note of the train of thought or the keywords that's needed and the keywords that's needed. Question 12. Question 12 you hear is on the on electricity. Okay, especially on particularly on practical electricity. Two core cable. Two core basically means there's two cable inside. Okay, the potential difference is 240. Power is 2 kilowatts. Okay, so same thing, wire 1 and wire 2, I will not do too much. You're supposed to take note of the cable. Live wire, what is the color? Blue color. Blue color refers to the neutral cable. Brown color refers to the live wire. And of course, if I have a third cable, which is the earth cable, what is the color? Yellow and green. Okay, so take note of it. Power, standard formula, power is IV. So if I know the power, if I know the current, I don't know the potential difference, I will be able to calculate the current. Here, take note, okay, of the SI unit. The question given is 2 kilowatts. So if I use SI unit, okay, remember, if I need to use formula, okay, it's always has to be SI unit. There's only two formula that don't require SI unit, and one of the formula it happens to be in what we call your practical electricity, which is energy. Okay, sometimes energy, when we talk about practical electricity, I talk about costing kilowatt hour. So when I want energy to be in kilowatt hour, power has to be in kilowatt, not SI unit. But in other aspect of the formulas, for other aspect, like example, power equal IV. Okay, all the factors has to be in SI units. So my 2 kilowatt has to change to 2000 watts. Okay, SI unit, so I'll get 8.33. Same thing, the next, if you look at fuse rating, the fuse rating I have is always the next best rating, the next highest rating, get the next possible rating, get the, okay, or the next possible or the next higher rating. So if 8.33, if you look at the ratio, okay, the next possible fuse rating I'm looking at is not 9M, it's not 9M, it's actually 10M. Okay, but of course, sometimes we are being linear, we accept 9M. But if you look at the textbook, the commonly available rating is actually 10M. Okay. Then same thing, like I mentioned before, the SI unit. Okay, so now I deal with the formula energy equal to power times time. But here I'm looking at energy in terms of costing, which means energy, it has to be, the unit for energy has to be in kilowatt hour. So which means that my power has to be in kilowatt, my time has to be in hour. I purposely change them to these two units, which are non-SI unit. Okay, because costing is always in terms of kilowatt hour, 30 cents per kilowatt hour. So I need to calculate my energy in terms of kilowatt hour first. 20 minutes, I convert to hour. Okay, I'll get 20 over 60. So I'll get the kilowatt hour to be 2/3 kilowatt hour multiplied by 30 cents. I'll get 20 cent cost. Okay, then part E. Okay, part E, same thing, metal casing, 2 core again. Okay, but now what happened is, okay, I have a 2 core casing. Okay, I have a 2 core cable, but I have a metal casing. When you talk about metal casing, the moment I highlight to you about metal casing, very often is what we call, we are looking at a earth fault. Okay, And when does earth fall occur is when the live cable touches the metal casing. So this is the first keyword I'm looking for. Okay. So when high current touches the metal casing, the current will actually flow into the casing. Okay, which make the casing to be high potential. And because of that, I can to get electrocution. Okay. And because of that, so what's the precaution that I need to have is I need an earth cable. I need an earth cable. It's connected to where? Connected to metal casing. Okay, remember when we talk about earth cable, we talk about earth fault, we always make references to the metal casing. Okay, so you have to tell me where I connect the earth cable. Having the earth cable is not good enough. I have to make sure the earth cable is connected to the right place, which is the metal casing. Okay, so take note of the wording, take note of the phrasing also. Now, question 13, I would say is the one of the unique question here. Okay, it's about turning effect. The hinge is here, which is the pivot. The forces is a bit slant, is a diagonal forces. Yeah, but one good thing about this is that they actually mark out all the perpendicular distance for you. The perpendicular distance for P is actually 0.72. So this one is actually what we call your perpendicular distance for force P. For your force P, yeah. So force P together with the perpendicular distance with respect to the hinge or the pivot, I will actually have a anti-clockwise moment. I will label it as MP. As for F, the perpendicular distance is actually here, mark out here. This is the perpendicular distance DF. Okay, and the moments about the hinge, about the pivot, it will be a clockwise moment, which is MF. So the two forces, F and P, actually leads to two moments, one clockwise and one anti-clockwise, which is what we label as MP and MF. Okay, so now we are ready to answer the question. Huh? So now, okay, we look for the moment of P, force P. So moment of force P is F times D. I need the force, I need the perpendicular distance of P, which I have prepared already, which is here, 0.72, oh, sorry, wrong ink. Okay, which is 0.72 force P. Okay, and given force P is 25 Newton. So it's just a simple substitution of the number. I will get a 18 Newton meter, and I know the direction to be anti-clockwise, like I mentioned before. Okay. Now the definition, not much of an issue. Okay, definition, not much of issue. Take note of the keywords, especially when you talk about principle moments and moments. Don't mix them up together because we sometimes tend to mix up these two definitions. For principle of moments, take note, okay, one of the keywords or one of the important words that we have to tell students, we have to include equilibrium when the object is in equilibrium. And the clockwise and anti-clockwise has to be always with respect to the same pivot. Then it makes sense. Okay, you cannot have more. It won't make sense if you refer the moments to different pivot. It has to be about the same pivot. Okay, so question 12. Okay, the part B is a scalar vectors. Okay, so I will not dwell much. Part 1 is the standard differences between scalar and vector. Circling the vector, yeah, okay, you can circle. I would say that you shouldn't be making any problem. Okay, displacement is vector, force is vector. Okay, only these two things is vector only. Time, length, mass, okay, distance, they are not vectors, so take note of it. Okay, resultant force act on the satellite. Okay, now take note for circular motion. We always like to give this moving circle. This thing has a name, it's called circular motion. Okay, it's just object moving in circle. Okay, it's a circular motion. Circular motion, the common question is, the common aspect is we always say is it always travel at constant speed. So it's a constant speed. But the interesting thing is that it's always having a changing velocity. It's not a constant velocity, it's a changing velocity. Because, okay, for me to go in circle, okay, I have to change direction every instances for me to travel in circle. If I don't change, right, if I don't change any direction, my satellite will actually just go straight all the way. So to prevent me from going straight, to allow me to turn in circle, I will need to exert a force. There will have to be a change in your speed direction. Okay, the object direction, sorry, your object directions. And when there's a change in your direction, okay, even though the speed remains the same, the velocity of the object will change, because velocity Okay, the difference between velocity. Velocity is like a scalar. So I can actually say that velocity actually includes speed plus a direction. So my speed can be remaining the same. It can be the same magnitude. But if my direction keep changing, my velocity will keep changing. Okay, because vectors is referring to, okay, velocity. Okay, velocity is a vector, it has magnitude and directions. Okay, so because of that, okay, because that's what I mean by because the satellite has to move, has to change direction to move in the circular motion. It has to change direction, which means that for me to change my direction, I will definitely need to change. I will need a force, okay, to bring about this change in direction. So as a result, okay, when I need, so there will definitely be a force acting on the satellite, okay, to bring about the change in direction. And when there is a change in direction, for example, okay, there's a change in direction. So when there's a change in direction, okay, this will lead to what we call a changing velocity. Okay, so when there's a changing velocity, this will lead us to infer that there is actually acceleration. Okay, and this will actually tell us there is actually a force acting on the object itself. Okay, so this will be the last segment on this particular question here. So if you look at the for this section B, choosing the 3 right question will actually be most important. Okay, if not, okay, this is where I end off. Okay, same thing. Okay, if you want, I'll be uploading some other paper also, or be some other notes. Okay, if you want to take, want to be notified of the of any videos I upload or any changes I upload. Okay, remember to subscribe to my channel, and also remember to like the video and actually to activate the bell function so that you get any notifications whenever I upload the video. Okay, if not, okay, have a great weekend coming. Okay, enjoy your day, enjoy your holidays. Okay, and be prepared for your O levels. Okay, see you.